Good morning, everyone, and welcome to Teledyne ISCO's August Pumps webinar, focusing on the world of reciprocating pumps. Today, Nick Daddabbo will be leading the discussion. If you have questions or comments throughout the webinar, please use the chat function within WebEx, and we will acknowledge all questions at the end of the webinar. At this time, I will turn it over to Nick.
Well, good morning, good afternoon, everybody, or even in some cases I would say good evening. I'm going to take some of your time today and talk to you a little bit about the world of reciprocating pumps and just give you a little basic background education on those. First and foremost, I do want to kind of give a little background and introduce myself. I am the Pumps Product Line Manager for Teledyne ISCO. I have global responsibility for all of our pump business. And just as a little side note, if you see my name, people are like, how do you pronounce that? Well, it's Daddabbo, but that's, makes it easier to see it in words to pronounce it. I've kind of been in the business line management, product line management world for just about 17 and a half years, going on 18 years in many different, I won't say too many, but many different organizations, mostly centered around pumps. Xylem, ITT, Big Gould's Pumps, IDEX, SPX, and roughly about 12 years of that 18 years of business and product line management, I have been in the pumps business, working in multiple industries like oil and gas, pharmaceuticals, chemicals, food and beverage, and plastics. So, seen a lot of different areas, different types of pumps and different places to go for pumps and different technologies. And I want to share some of that. I've shared that with our organization. I want to share some of the great things about reciprocating pumps with our organization. So that being said, let's get into and talk about pumps themselves. Before we get into reciprocating pumps, I really kind of want to get a quick overview of the pumping technology that's out there. And in the aspect that we're looking at pumps is more so on the R&D lab scale and then pilot scale. Applications. Many of these pumps will also work in small-scale production. Unfortunately, we do not get into the larger scale production like you'd find in your large oil and gas facilities, but some of this technology does play across the board at all three or all four of those types. So the first one is one we're all very familiar with here in Teledyne ISCO, and that is syringe pump technology. And this is not the tabletop syringe pump type. This is more like a desktop. This is a larger size. When you look at tabletop, that would be more your Harvards, your Katie Scientifics, your Chemex. Similar technology, similar design, but the capabilities and the pressure ratings and the flow rates vary greatly between the ones we're talking about here, et cetera. When you're looking at overall pumps and what you need when you need to move or pump fluid or material, the advantages here on the syringe pump side is the design pretty long lasting. When you look at and purchase a syringe pump, it is very durable. It will last a very long time. I can tell you the pumps that we have that are syringe pumps, some of them have been running consistently for 25, 30 years with just maintenance, just minor maintenance needed. So it's a very durable design, as close to absolute pulseless as you can get. Without the addition of a pulse dampener or any other external technology. So if pulsation in moving material is an extreme critical need or a critical issue for you, and you need it to be pulseless, you want to look at syringe pump technology. Very precise flows, higher pressures. Some syringe pump technologies can get into the 40,000 psi. Disadvantages here is an initial investment is relatively high at times. The ROI does drag out a little longer. You're not going to get your 2 to 3 year ROI or 5-year ROI in some cases because the investment's high and it takes longer to get that recoup that money. Most of the time you'll find that they'll have large footprints also. Some of the competition, some of the other syringe pump makers do have them that are somewhat about the size, the footprint of an 8.5 by 11 sheet of paper. So that's not bad, but it is larger compared to other pumping technologies that are out there. And we'll touch on that just real shortly. So that's syringe pump technology. I don't want to spend too much time on these different things, but it puts it in perspective when we're looking at overall reciprocating pumps. Peristaltic pump technology is the next one. Some of the advantages are there's no wetted parts. The fluid stays in the hose or the vehicle that is rolling, and there's low contamination risk. The only risk is if the hose starts to leak, which it can happen over time. If you look at a disadvantage, the wear life varies on those depending on the material you're flowing, the rate that you're using the pump at, and the material that the hose is. So there's a lot of different variables to consider, even just in the hose itself for this technology. You can get sanitary hoses available for food and beverage applications, so that works out kind of nice. So when you're doing your wetted surface area analysis for FDA, et cetera, you're focusing mostly on the hose. Very easy maintenance. The design in the market space for peristaltic pumps, sometimes you can click the head off and click another one on in about 30 seconds or maybe a minute and a half. So very low downtime. Disadvantages, it's not pulseless. You can see how the rollers roll over the hose. There's going to be squeeze, space, squeeze, space, squeeze, space. So you're going to get a pulse, a beat, a regular drum beat. And over time, peristaltic technology does have to be calibrated. It does lose some of its actual accuracy over time if the pumps are used a lot or used at a high rate. So that's a risk that you take. That being said, this technology is still very reliable, and it's a good general purpose type technology. Gear pumps, kind of similar a little bit from the standpoint of how they're functioning. The gear is just moving together, and the fluid goes around the gears, either it goes around the outside, so you get a suction, and it creates a little suction and discharge. Really good with viscous fluids. Viscous fluids are good with, particulates they're not. Particulates will increase the wear on the gear, which you can sometimes get metal filings in your fluid, et cetera. You have to be very, very careful about that. Viscous fluids, I mean, they're a gear, they're very strong, so you have paste or jelly coming through there, that'll work very well. Low capacity, higher pressure. It is bidirectional, so if you have a need to use your pump in a two-way manner, this type of technology does work very well with that. Does not have the ability for precision flows. It is pretty much a material or fluid moving style technology. Diaphragm pump, so this pumping technology is very similar to a reciprocating pump, but you add in a actual diaphragm. You can actually see in the design it states they're reciprocating motion. So the diaphragm provides a flat surface that pushes out more fluid up pulls in from the suction discharge, pushes out more fluid that way. It is less expensive over time. It does use less energy, and there's low risk of leakage, except for if the diaphragm breaks. But many of the diaphragms are made out of very, very durable Teflon or type of material that is tested to go for thousands and thousands of pumps. It does struggle with particulates. The check valves do get gummed up, and you have to keep prime on it. And that's if a diaphragm pump loses prime, it loses its effectability to perform well. So that's something to keep in mind. So these types of technologies we've looked at here are just the different ways to pump material. So I want to be sure that I wanted to cover these real quickly so we can kind of go and compare it against reciprocating technology. So as we move along here, let's get into reciprocating pump technology. I keep tossing around the word technology, and it's really just how the pumps are actually working. So did you know, I wonder how many people on the phone here actually knew, that ISCO first created our reciprocating pump in 1983. So that's 35 years ago. It was designed basically for HPLC, but other customers found it works pretty well in chemical and oil and gas. So it was reliable. So they started to get very interested in it. You know, it was very early on. We had patented technology for smooth, constant flow. Not really typical of the pumps that were there at the time. It was really a groundbreaking pump for us. And it was something for us to, a little different type of a pump than we currently had sold. So that being said, let's define what a reciprocating pump is. Now, you're going to hear that these have, when you talk about a reciprocating pump, lots of times they're equated to a piston pump. That refers to the fact that there's a piston that moves back and forth, does a reciprocating motion. So you can call them recip pumps, call them piston pumps. There's types of pumps out there that we do not deal with, that we're not talking about in this space, that you're going to see. I typically know them as plunger pumps, extremely high pressure and fast moving, and there's like 2, 3, 4 heads to one pump. That is not in the class of reciprocating pump that we're discussing today. But let's talk about, there's 2 different types of pumps, namely dynamic and positive displacement pumps, from the pumps world in general. When you're referring to a dynamic pump, you're speaking mostly about a rotating element, or rotating either a vane or impeller that is moving fluid and creating pressure. That is a dynamic pump. Positive displacement pumps, or PD pumps, are reciprocating and somewhat on your lower level rotary types, which would be like your gears and your et cetera. So the reciprocating pumps we're speaking of are basically positive displacement pumps. And the true definition of a reciprocating pump, very, very simply, it's a pump that uses a backward and forward motion to move a fluid or a material. Kind of think of a train, how the old train engine used to chugga all along and the bar would move the wheels. Basically, that's all that's happening. A piston or plunger or diaphragm moves forward or backwards. Very, very simple. Very, very simple motion. Very simple to understand, and a very simple design. So that's how it, from the standpoint of how you speak about it. This slide here has got 3 different pictures on it, and the one on the far left kind of shows you the parts of what would be considered a reciprocating pump. You can see on the upper one, the suction is created when the motor pulls the piston out, draws the fluid in from the outlet, in from the inlet, and then as the piston pushes back, it pushes the fluid out the outlet. You'll see the blue arrows there. Very simple design, very easy to understand. You know, obviously, every reciprocating pump is different in amongst itself. So this is the basic of the pump. People may put other things in there to make it work better, smoother, patented, have a better seal, protect against different materials, et cetera. But these are some diagrams that give you a little bit of an idea of how things work when it comes to the inside of a reciprocating pump. In the lower right there was a little animation that just basically shows you how it works. So it's a very, very easy design to understand. Okay, so this graph right here, when we're talking about the use or movement of a reciprocating pump, this is we did a test on a reaxis at a very slow rate with 1,000 PSI. And this gives you, it looks broader than it is, but if you look at the scale, it's the milliliters per minute are it's very broad, very wide, with just a changing with 2 milliliters per minute. So this is kind of a drumbeat motion, and when you talk about a drumbeat, just a regular up and down, in and out, very simple, very low. So that's what this picture gives you an idea of. Now, this is just an average generic picture. Obviously, flow rates can change this, PSIs can change this, materials, et cetera. But when you're looking at the motion or thinking about the motion of drawing in, pulling out, drawing in, pulling out, this is how it looks on a chart to give you a better understanding of it. Okay? So there's some key considerations when you're looking at or thinking about specifying a reciprocating style pump. Okay? For instance, here, a very interesting thing you have to consider is if you're going to use a single head or a dual head. Single heads are very good for just transferring fluid, moving something from vessel A to vessel B or vessel A to reactor B. When pulsation is not a concern, this is the great way to go. You can add a pulse dampener if you so need to limit the pulsation. So I don't want to say it's not a concern, but if that does come up, and you know, it's a very simple workhorse style design for a reciprocating pump. Lots of times we'll talk to people and we'll have people that use multiples of these to move different chemical agents or chemical reagents through a flow chemistry application, that all they need is just to move it in there at a steady rate. And it's got to come in on the left side at 10 mils a minute. It's got to come in on the right side at 5 mils a minute, and then it's got to come in from below at 3 mils a minute. So it just gives you, it's a very nice, even flow, okay? When you look at a double head, now this gets a little more functional for you. If you need continuous flow, and so the single head would be great for, I would say, batch applications, but people do use them for flow chemistry applications. Dual head or double head is more appropriate for your continuous flow because you have the dual heads, the pulsation rate is much, much less. And if you add the pulsation dampener into this product or into a reciprocating pump, whether it be internally to the pump, because you can add those internally, or you set one up externally within the process flow, you're going to really limit the pulsation. Again, it won't be as strong as a syringe pump technology, but it gets really close, really, really close. One thing I would recommend, too, is just as a consideration, I know we're talking about reciprocating pumps, but when you're looking at adding in external pieces to the pump, whether it be a pulse dampener or something else, you want to consider the total cost for all of that versus other technologies out there like syringe pumps. But for this application, dual-headed reciprocating pumps are very strong, very solid. A couple other things to consider here, too, is there's variations within the style of motor, the type of motor that moves the piston back and forth. In our group of product offerings, we have two types. We have a direct drive. It's just a linear motion. It's a rotating motor shaft. Simple range, cost-effective, but cannot do a lot of the higher pressure capabilities when you get into the 5,000, 6,000, and 10,000 PSI or even more from this type of pump. So this would go well with your more general purpose type pumps. In our class of offering, it would be our M1 or be the LDEX Optos, so those type of things. Just a pump moving fluid. It's all you needed to do. It doesn't need a lot of pressure. So when they're focused on the lower flows and the pressure isn't a concern, you're going to see more direct drive mechanisms, so keep that in mind. Belt-driven gives you the capability to get a lot higher pressure capabilities just because it's like a belt and pulley configuration that's attached to the pump motor right to this camshaft. So it's going to give it a little more hydraulic capability to handle higher pressures. In our product offerings I'm showing, we talk about the LD, the LS, and the PR. Those are better suited for those needs. So when you have higher pressure but lower flow that's needed, or even higher flow, the belt drive products would be more that you'd want to consider. And these will come out with questions you ask your customers, which we'll kind of review at the end of this presentation. This is a lot of words, but really to pare down what is being said here is in many cases, reciprocating pumps can do either constant flow or constant pressure. And you can use it to, as an example, reciprocating pumps like an LDEX or a Teledyne ISCO can be used to provide pressure in a rotational molding in the plastics market. So if you've got a rotational mold happening, one of the big issues that the plastics manufacturers have when you're using that type of process is the material does not always get to the full end of the molds and all the crevices that are designed into it, because some of these plastics designs or some of these parts and pieces designs today are absolutely intricate. So to getting the material all the right spots needs a little help. In this case, a constant pressure pump would provide the pressure to push that fluid so it makes sure as the mold is rotating, the pressure stays in there, and it pushes the material to all the crevices of the mold. So it fills out the design well. So that's a great method for that. And in the same world, let's keep talking about that constant flow. When you're looking at a plastics market or an extrusion market, constant flow reciprocating pumps can steadily produce and push in colorant or UV protectant or some type of chemical that gets mixed in with the extrusion so the final product has some protection or color or variation in it. Perfect, just steady flow. Goes back to, I talked about a kind of a generic multi-purpose pump. Constant flow pumps will do that very well. But when you're looking at reciprocating pumps, you need to figure out in your application, do you need a steady flow. And again, that goes back to the first slide talking about a single head or a dual head. Do you need a really straight pulseless flow, or do you need just a steady flow? Then if you have a constant flow need, there you go. There's your type of products you want to use. But if you determine you need pressure, this is something you need to consider and need to look at and make sure that the product can actually do that. Okay. Wetted materials. You know, there are many different materials out there. Some of the most common ones that you would use in the fluid path. Often in reciprocating pumps, you're going to see synthetic ruby, synthetic sapphire, so fluoropolymers are included in the full process, in the full fluid path. But also you're going to have options for the heads and with the containment of the fluid path be stainless steel. That's your most common, and you'll see it an awful lot in HPLC processing and metering applications. You know, if somebody talks about needing to use or move highly corrosive materials, Hastelloy is definitely the second most popular out there. Stainless steel works well with some corrosion resistance, but your more aggressive stuff, you want to make sure your fluid path has Hastelloy in it to protect against damage. Now, that being said, there are other materials that manufacturers use for the fluid path in reciprocating pumps. Titanium's an option when you really need something to protect against aggressiveness. Or PEEK. If you were worried about leaching of the metal into the material or the fluid that you're pushing through the system, this is very common in the pharmaceutical market, as is Hastelloy. You get some very aggressive materials when you're creating pharmaceutical drugs or medicines. So you want to consider and think about the wetted materials. So far you want to find out if you really need a steady pulseless flow or more of just a general movement, if you need pressure, constant flow, or if you need higher pressure, lower flow, or lower pressure, lower flow. And then you also want to think about the wetted materials. These are things that you have to consider when you're selecting any type of reciprocating pump. And for that matter, it really isn't a bad thing to think about these general commentary when you're looking at any pumps. So other options, there's some manufacturers out there will offer jacketed heads on the pump. So those would be either the cooling mechanism or a heating mechanism. And you see this lots of times with when you're moving viscous fluids. There'll be an external circulating bath that gets connected to the secondary cavity to heat and cool the pump head. So as the fluid comes through, if it's heated, it makes it more viscous so the fluid can move freely through there and continue through the process. Cooling can be if the liquid is coming in extremely hot. You want to make sure that you have the capability to do that. So this, again, you have to consider your application and what you're trying to move, what you're trying to look at, and what you're trying to do with it. Okay? So let's talk about just very high-level advantages and disadvantages, because your application and your material you're going to use can drive more additional advantages or disadvantages. But let's talk about some of the higher-level ones. So advantages, with reciprocating pumps, you can get higher pressure, lower flow. You also get lower pressure, lower flow, as we talked about. But you can get into 10,000 PSI, some cases 25,000 PSI, at a much lower flow rate with a smaller footprint than other types of pumping technology. So that's a consideration. You want to look at the fume hood or where you're putting this pump or the space you're going to need it on the desk in the lab. It all comes in the conversation. As we stated, it's capable of constant pressure, constant flow. That's very important to know that there's a lot of flexibility with a reciprocating type pump. A very proven common design. Reciprocating pumps, whether it be the standalone box pumps or the heads that people use, they put them in the other machines. This happens quite a bit in the chromatography world, where people will just take the heads and need to move fluid for the chromatography application. They just build the head into their standalone system. So this design has been around for a long time. It's a very common basic design. Steady, reliable performance. You don't need to recalibrate a reciprocating pump. It's there. It's just you can turn it on and let it run. Minimal maintenance needed. Sometimes you got to change the seals. or change the heads even. And typically these designs are cost effective. If you're having budget constraints, many times we've talked to customers and they have a specific need in a flow rate, a pressure, et cetera, what their stated need is, and many times that pump is going to be, that type of a pump they require is much more expensive or is a little out of their budget, so they come to us and say, what's another option? So we say, okay, well, we look at these types of reciprocating pumps that we offer or there's out in the market space. If you need this flow rate or this pressure, we can get there. Or we can't get there with the pressure you need, but we can get there with the flow rates. Do you really need that much pressure? Sometimes, the customer, actually very often, a customer says they need 2,000 PSI and they only need about 1,000 or 1,500 PSI, but they'd like to have the cushion to be able to go up if they want to adjust their application or experiment. So these are things that have to come out in a conversation, but there's a reciprocating pump is a very reliable and good option for our customers. So disadvantage. In many cases, it does struggle with viscous fluids, this type of technology, unless you add the jacketed head. So that's an additional cost you always have to consider. Check valves, check valves, check valves. We've all lived with the fact that check valves get gummed up and get sticky, especially if there's even minute particulates in the material being pumped. That can be a headache at times, so keep that in consideration. Particulates might not be a great thing to move through this technology. It's not pulseless, but you can add a pulse dampener either internally or externally to get it pretty close. But again, like I said before, can make sure you consider the overall cost of what you would have to be adding before when you look at this technology. And then sometimes there's some limitations of pressure limits. A standalone syringe pump can get to 30,000, 40,000 PSI. Not sure you're going to see those levels in this type of pump here. I think the design limits of this style of technology is in the 20 to 25,000 range, but probably closer to 20. So there are some disadvantages. Granted, there's probably a lot more disadvantages and a lot more advantages based on the application you have or the things that you look at as being important to your application or to your design. But this is the higher level advantages and disadvantages. So there's many applications out there for reciprocating style pumps. HPLC chromatography world has been using these pumps for years, and they're all over the place, either in standalone systems or in the box themselves. You'll see them all over the place. Oil and gas uses them. Oil and gas uses them all over the place. I've been in a few labs where I've seen 10 or 20 of these things stacked on a rack. So it's very popular use in the oil and gas world. Constant pressure for rotational molding I just mentioned. Any type of continuous processing or flow chemistry application. These things they're workhorses, they're good, they'll work for you. And then we talked about dosing and color into plastic extrusion machines. There are so many different applications here, and there's probably a bunch of them that I haven't considered yet that other people have done, and I know there's research out there on Google Scholar that people have used reciprocating pumps to do different things. So the possibilities are endless with a reciprocating style pump. It's just finding the right one when you walk through all the considerations that we just talked about previously. They're important when you're helping pick or select a specific model or manufacturer of a pump. We do have one piece here. We have one application that one of our engineers and chemists have designed using a reaxis, the original reaxis we have. This is just one thing. This is azide reactions used for flow chemistry. You can see the results there. You can see the diagram very simply. Use 2 of these reciprocating pumps to get this done. Very easy application. There are hundreds of these, available on Google Scholar, how to use a reciprocating pump for different chemistry or applications. So I highly recommend out there, look at reciprocating pump technology. You can Google reactors, you can Google the specific vendor names, but I'm telling you, that's a great source for applications there. And I'm sure you all have a significant amount of applications yourselves. So lastly, I want to close out with this, I want to talk about a slide that as you're talking to your customer, basically I would call these qualifying customers, qualifying questions, but these are things I would ask the customer to help them decide which pump they need or what type of pump they need that we offer. But these are things you should ask yourself when you are laying out or designing your application or your experiment or your production line, you want to ask yourself these questions so you consider all this stuff. So when you have somebody like myself coming in, or one of our sales reps, or another company's sales rep or vendor coming in to talk to you about pumps, it helps guide that person to find the right reciprocating pump for you. So again, what type of process? Is it an R&D? Is it scale pilot? Is it small scale production? Those are important things, because we talked about the capabilities of reciprocating pump technologies. How much room do you have where the pumps can be installed? Reciprocating pump technologies, typically smaller footprints, maybe less than the size of an 8.5 by 11 paper or 11 by 17 paper, but you want to have that understanding, because even within the reciprocating pump technologies or pump offerings that are on the market, you can actually have different footprints there too that might work for you. What's the flow rate and pressure needed? This goes back to belt-driven, or if it's a constant flow that's needed, or the type of pump, or the capabilities of the reciprocating technology. Viscosity of your fluid, as we talked about, reciprocating pumps really kind of struggle with viscous fluid. So, unless you need to add in a jacketed head. So if you're saying you're going to be moving molasses through this line, you're going to have to probably have something to heat up the material, either be externally or internally to the pump, to help it move through quicker. You want to keep that consideration. Does it require corrosion-resistant wetted materials? Again, that can be very important to tell the customer, tell the manufacturer's rep or vendor that you need that. Does it need to be heated or cooled? That goes back to viscosity, but it also goes with keeping the material in the state that it's in. In different chemicals, when they mix together, if the temperature changes, you get a different reaction than you do if it's hotter or colder. So if that's important to your design, the design of your process or your application, you want to make sure you have that consideration and look at the right reciprocating pump. Okay? Does your fluid have particulates? Well, as we walk through the pumping technology, that we know there were certain ones that just do not do well with particulates. And as we're getting into check valves on many reciprocating pumps, you're going to want to walk away from something. You're going to want to change your mind, or at least consider the fact that could be an issue down the road. Is external control required? That's just good to know, because are you going to run it by a computer? Are you going to need a controller, et cetera? What software do you use? You want to be able to understand that the pump you're looking at will connect to like Mettler's software, or your back-end enterprise software that you're using. And then what's the max pressure reaction? Are you pumping anything through pack catalyst? Those are things you just want to have. You want to walk through and have these and understand these as just little fact sheets when you're looking at and trying to choose the correct reciprocating pump or type of reciprocating pump out there. Okay? So that being said, I'd like to open this up to questions, and I have a few people in the room here. So, well, in the nature. So the first question is, can a reciprocating pump withdraw liquids like fill refill? Dale, I'm looking.
No, it's Dale Clay. The reciprocating pump has such a small volume that there's not enough volume to really do a refill like syringe pumps.
Yeah, so syringe pump technology is probably a better one to use for withdrawing liquids. Okay. Next question is, can this pump maintain constant pressure for a system?
Yes.
And I think
constant pressure.
Yeah, and I think as we talked about, constant pressure mode is definitely an option that you want to consider. And this one's, especially the ones we're talking about here, this technology has that capability. By the way, I have Dale Clay in the room here. He's our product line manager here for pumps. He has many years of technical expertise with us, so we've got a good team in the room to answer your questions. With that, let's see. Are there any other questions out there? You can use the chat feature, or you can just ask us on the phone if you like. Okay, so I know we're all busy, and I really appreciate everybody's time. I think what we're going to do now is we're going to end the webinar. If you have other questions that come, feel free to send an email to us, and it'll get routed to myself and or Dale Clay, and we will get an answer back to you very quickly. I do appreciate your time and your attention. I hope you have found this to be at least somewhat informative. And we're here to help you find the right pump for your process and your application at any time of the day.
Thanks, everyone. This presentation will be available afterwards. We will be sending out an email with a link to the presentation. And again, if you do have any questions after the webinar, feel free to reach out through your original invitation to the webinar or to Nick or Dale directly. We appreciate your time this morning and have a great day.
Thanks, everybody.